You know when you look up at a big, fluffy white cloud and just watch it drift by? It seems so light, so peaceful, like a giant puff of cotton. But that calm picture is actually hiding a huge paradox, one that seems to break one of the most basic rules of physics: gravity. Okay, so get this. An average run-of-the-mill cumulus cloud, the classic puffy kind you see on a sunny day, weighs about 500,000 kilograms. To give you some perspective, that's the same weight as 100 full-grown elephants, just hanging out up there.
And that's our mystery, right? We're all taught that what goes up must come down. It's gravity 101. So how in the world does 500,000 kilograms of water just float? It doesn't seem to make any sense. Well, today we're going to crack this case, this apparent crime against physics. To solve this, we've got to treat the sky like a crime scene and start looking for clues. And the first thing we need to realize is that our gut instinct that something this heavy should just crash down to Earth is based on a little bit of a misunderstanding. That's it right there. The key to this whole thing isn't the total weight itself, but how that massive weight is spread out. And understanding this is our first big break in the case. So our first clue is all about what I like to call the illusion of mass. We're about to see how something can be unbelievably heavy, but act like it's almost weightless. And it all boils down to the huge difference between weight and density. This really gets to the heart of it. On one side, you've got the total weight, that staggering 500,000 kilogram number. But on the other, you've got density, which is all about how much stuff is crammed into a certain amount of space. A cloud is incredibly heavy, sure, but it is not dense at all. Think about it like this. Imagine you have a 1-ton rock. If you drop that, it's gonna fall fast and hard, right? It'll leave a crater. Now, imagine you take that exact same rock and grind it up into a super fine dust. It has the exact same weight, but what's it gonna do? It's just gonna float around and disperse in the air. And that is exactly what a cloud is. It's the dust in our analogy. The weight of those 100 elephants is spread out over a gigantic space. We're talking over 1 billion cubic meters. This makes the cloud as a whole just barely denser than the dry air around it, so it doesn't plummet like a rock. But believe it or not, that's still only part of the answer. All right, time for our next clue. For this one, we have to zoom in, way in, because the cloud isn't one solid thing. It's actually a massive swarm of trillions of tiny individual suspects. See, a cloud is made of these things, microscopic water droplets. Each one is, on average, just 20 micrometers across. That is ridiculously small, thinner than a strand of your hair. And when things get this tiny, the rules of physics start to act, well, a little weird. It really comes down to this relationship between mass and surface area. Gravity, of course, is pulling on the droplet's tiny mass, but at the same time, air resistance is pushing back against its surface. For something this small, its surface area is enormous compared to its mass. This means the air basically acts like thick syrup, creating a ton of drag. This constant battle between gravity pulling down and air resistance pushing up leads to something called terminal velocity. It's the top speed an object can reach when it's falling. For a bowling ball, that's pretty fast. For a feather, it's pretty slow. For a tiny cloud droplet, it's basically nothing. The terminal velocity of a cloud droplet is just 1 single centimeter per second. That's it. So yeah, technically every single one of those trillions of droplets is falling. But at that ridiculously slow speed, when you're looking out from 2 kilometers below, they look like they're not moving at all. But that brings up another question, doesn't it? Okay, so it's slow, but it's still falling. So over time, shouldn't the whole cloud just gently drift down and settle on the ground like fog? Well, it would, except we're missing our third and most crucial clue: an invisible force that's constantly fighting against gravity. It turns out our little falling droplets have an accomplice, an unseen force that's always giving them a lift, basically putting them on an escalator that's going up way faster than they're trying to fall down. And this accomplice is called an updraft. It's a pretty simple idea, really. The sun heats the ground, and that ground warms up the layer of air right above it. And as we know, warm air is less dense than cool air, so it starts to rise. This creates a powerful, invisible elevator of rising air, right in the spot where clouds love to hang out. Just look at the numbers here. It's a total mismatch. The droplet is trying to fall at this leisurely pace of 1 centimeter per second, but the updraft is shoving it upwards at 2 to 5 meters per second. It's not a fair fight. It's not even close. The updraft wins, hands down, keeping the whole cloud floating or even pushing it higher into the sky. But wait, it gets even cooler. The cloud isn't just a passive bystander getting a free ride on this updraft. The very act of the cloud forming actually adds fuel to the fire, making the updraft inside the cloud even more powerful. This is the cloud's secret engine. See, when water vapor, which is an invisible gas, cools down and condenses into a liquid water droplet you can see, that process releases a tiny puff of energy as heat. We call it latent heat. Now, multiply that tiny puff of heat by trillions of droplets all forming at once, and it actually warms up the air inside the cloud. This makes it even lighter and more buoyant, which basically turbocharges the updraft. Okay, so if this whole system is so perfectly balanced, why does it ever rain? How does gravity finally win this fight? Well, it all happens when our tiny microscopic droplets stop being so microscopic. The whole balance of power is about to shift. The process that does it is called coalescence. Inside a cloud, it's a pretty chaotic place. Those trillions of little droplets are constantly swirling around, bumping into each other and merging. One droplet combines with another, and then another, getting bigger and heavier with every single collision. And this is the tipping point. Through coalescence, a tiny 20 micrometer droplet can grow into a 2,000 micrometer raindrop. That's 100 times bigger. It's not a tiny speck of dust anymore. It's starting to become a little rock. And that change in size has a huge impact on its speed. Its mass has grown way faster than its surface area, so air resistance doesn't have nearly as much effect. Its terminal velocity just skyrockets from that pathetic 1 centimeter per second all the way up to 10 meters per second. Now it's finally heavy enough and fast enough to punch through the updraft. Gravity wins, and it starts to rain. So, when you get right down to it, clouds don't defy gravity at all. They aren't magic. They're just a beautiful, perfect example of a system in balance. They are simply enormous collections of microscopic particles whose individual, tiny falls are totally overpowered by the powerful currents of warm air they're surfing on. It really makes you think, doesn't it? The solution wasn't just one simple thing. It was this elegant dance between density, tiny scales, and thermal energy. It makes you wonder, what other amazing, dynamic ballets are playing out all around us, hidden in plain sight?